Hi everyone, I'm Andresa Souza Ribeiro from Federal University of Santa Catarina. I'd like to take this opportunity to talk about the experimental characterization of the flow structure in accelerated bubble flows. This presentation will be made in accord to the summary. First, you have a short introduction about the topic with many papers about bubble flows, followed by the methodology and the results and discussion, conclusion, and finally the reference used in this presentation. Two-phase liquid gas flows plays an important role in chemical industry, transformation industry, oil and gas industry. However, this study is common in pipes flow, and when it comes to the bubble flow in venturi tubes, the studies are about gas phase. It don't present information about the liquid gas. For example, in the work of the Fujioka et al., the authors investigation the local void fraction profile, fluctuation velocity, and turbulent energy profile of liquid phase. However, in a pipe, the studies in other types of geometry, such in venturi tube, are focused in gas phase as velocity, size, and breakup of bubbles. So, according to the author's knowledge, there are no studies in the literature analyze the flow structure of the liquid phase in our water bubble flows in convergent divergent sections. Hence, the objective of the present work is to analyze the effect of the dispersed bubbles on the flow structure in liquid gas bubble flows in convergent divergent section. These results are most useful for validation of CFD model and accelerate bubble flows. This figure shows schematically the experimental setup. The water flow rate is measured by two flow meters. The liquid phase flow rate is controlled by a frequency inverter connected to electric water pump motor. The dispersed bubbles are injected at the bottom of the tube through a porous gas diffuser in order to control the size of the dispersed bubbles. The gas flow rate is controlled by a neutral valve and measured by 1 flow meter. A box was constructed with transparent electrode made with 8 plane faces at the PIV measure section, filled with the same liquid as in people in order to minimize the optical distortion. The figure is a photograph of the convergent divergent section. In applications to gas liquid phase flows, the presence of the interface skirts the light of the laser, which much more intense than these particles, impede the CCD camera to capture the signal particles. Therefore, the AEF technique was employed, using fluorescent similar particles and an optical filter in front of the camera lens. However, the fluorescent light emitted by these particles can be also reflected by the interface, leading to a bias in measuring of liquid velocity. Therefore, a discrimination technique was used, present in Cerqueira et al. The phase discrimination algorithm developed by authors used this work to remove these unrealistic velocity vectors by analyzing the PIV-LEF row images. The algorithm identifies the interaction windows occupied by bubbles and remove its configuration for the ensemble average of liquid velocity. The blue window represents the vectors of the liquid phase, and red window represent gas phase regions. For the PTV method, is based on backlight illumination footage, is used for obtaining information about gas phase such as velocity and bubble size. Furthermore, it's used also to verify the liquid velocity finds obtained from PIV-LEF method. The details of the image processing and application of PTV can be encountered in Cerqueira et al. And Cerqueira and Paladin. In this work, 2 single-phase flow conditions and 6 two-phase flow conditions are going to be tested. Table 2 presents the comparison of the liquid flow rate measured by flow meter and the numeric integrated value from the PIV liquid velocity profiles in light section. The results shows that the deviation between the two values is within the range of the liquid rotor accuracy, more or less 5.0% full scale. Then values the liquid phase from PIV method after phase discrimination algorithm are compared with values the liquid phase from PTV method. Can observe the results from both methods present excellent argument, showing that the phase discrimination algorithm and PTV for bubble tracking technique used in this work originates results. Then, the flow structure can be evaluated in convergent-divergent section. This figure shows liquid axial velocity contribution for laminar case and different case superficial velocities. At the inlet region, the velocity profiles tend to form a pike in the core region, which decreases towards the wall, indicating the presence of downward liquid film induced by liquid dragging by gas bubbles in core region, which more evident in higher gas thresholds. This downward liquid has been observed in mean axial velocity induced in Cerqueira et al. In convergent section, this downward velocity near wall becomes less intense, and when arrived at the trough, the opposite happens. Liquid velocities on core and upward peaks near the wall. The maximum liquid velocities near the wall could indicate the presence of bubbles in this region. The species do not have measured the void fraction radial distribution. In the divergent section, there are 2 regions of the liquid recirculation, pronounced and intense. The maximum velocity occurs in the central region. The figures shows liquid axial velocity distribution for turbulent case and different gas superficial velocities. For the case with high superficial liquid velocity, the liquid velocity profiles are also affected by the dispersal bubbles. However, picking a similar flow structure to single-phase case, opposed to what is observed for the lower value of liquid superficial velocity. The velocity liquid profiles in light region follow the same trend found in Liu and Benkoff, but in adult, where the velocity profile changes from flat in the single-phase case to convex as the void fraction increases, with a full increase of the liquid velocity in the core region. At the test section, there is an increase in liquid velocity in one radial direction, indicating that the gas flow. In other words, the amount of bubbles is sufficient to occupy the entire diameter along the test section, and in the divergent region has opposite happens in the case of lower liquid superficial. The continuous phase has no moment enough to form regions of liquid recirculation. This figure shows liquid axial fluctuation velocity distribution for laminar case and different gas superficial velocities. The result shows that a small quantity of bubbles in the flow results a significant increase turbulent fluctuations in the liquid phase. Until the zero are equal to turbulence in central region increase strongly with the increase of void fraction. The same effect was observed by Liu and Benkoff in a duct of constant section, in which bubble-induced turbulence is more pronounced in the core region. At 0R equal 5, a of bubbles not concentrated in UR. The maximum of turbulent fluxes occurs in this region. Such phenomena happens because the liquid recirculations at the divergent section result in a region of pronounced share, increase the production of the turbulent kinetic energy. According to Oxqua and Tomiwana, the bubble-induced turbulence exists even where the bubble concentration is very small. This is because the diffusion of the turbulent kinetic energy occurs from a high to low void fraction region. This figure shows liquid axial fluctuation velocity distribution for turbulent case and different gas superficial velocities. The presence of the dispersal bubbles promotes a relative uniform turbulence distribution, indicating that the gas bubbles promote a strong radial momentum transfer. So, in conclusion, we showed that the presence of dispersed bubbles in every low concentration changes dramatically the flow structure. For low liquid superficial velocities, with the appearance of the downward flow region in the core of the convergent section. For the cases where the liquid flow is laminar, the presence of dispersed bubbles generates a bubble-induced turbulence. in the wall test. In case of turbulent liquid flow, the increase of gas volume fraction changes the turbulence, which results as the sum of VIT and the liquid phase share induced turbulence. These are the references we use in this presentation. And I want to say thank you for watching this presentation, and I will be glad to answer any question that you have for me.